Hello everyone. In today's lecture, I would like to talk about the addressing modes. So addressing modes or the instruction formats and the advanced assembly is the major topics in this chapter, and we are going to cover these today. Addressing modes, instruction formats, the assembler operators, functions and directives, assembling and disassembling the program, which we already covered some parts in the previous lectures. Programming examples, macros that we use, EEPROM memory, how we can interact with EEPROM memory, and the checksum example are some of the topics that we will cover today. So if we start with the addressing modes, the CPU can access data in various ways. So this data, it could be in a register or in a memory or provided as a immediate value. Now, these various ways of accessing the data are called the addressing modes. And the various addressing modes of a microprocessor are determined when it is designed. So we cannot change that. So therefore, they cannot be changed by the programmer. Now, the AVR provides a total of 13 distinct addressing modes, which we are going to see in this chapter. The implicit ones, the immediate, direct, indirect, relative. So we can compare them by data addressing or the program addressing. So those are some of the categories that we are going to touch in a bit, and we are going to see an examples of different instructions which they belong to a different category. So if we give a start, we'll start with the implicit addressing modes. So this instruction, they don't have a source or destination. So it's hidden, it's implicit. So we can just have the instruction. There's no registers written over there. So this is a word by one word, and the cycles generally one, but some of these cycles are 4 or 5 cycles. And there's no operand, as we already said. The examples are like clear carry, return, no operation, break, LPM, SPM. They don't need any operands in front of them. And the machine code is 16-bit opcode. That's it, as we don't have any address or anything like that. So if we consider that, we can look at these examples given over here for the implicit addressing. So clear half carry, clear carry, set negative, put a microcontroller into sleep mode, return from subroutine, return from interrupt or no operation. Those are the some of the examples which is given for the implicit category. Now, if you look at their machine code formats, they all start with 1001, except the no operation one. And their part of the opcode is similar. So CLH, CLC, set negative, these are all status flag related. So their second part of the machine codes are also similar. And their third part is changing, and the fourth part is also exactly the same. So this actually help the microcontroller to deal with the opcodes easier. So we can see how they are differing. So the sleep, return, and return I, they have this 010, 010, 010, and only the last bits of those machine codes are changing. So this actually helps decoding hardware simpler. That's why we are using this type of, actually the AVR has using this type of coding technique. So this is the first one. The next that we are going to see is the single register direct. So when you say single register direct, its instruction has one GPR address and nothing else. So that's the source operand, and the destination is the same register. So it's a one word, it's a one cycle, and the operand can be any single register. Negate R20, complement R16, decrement R5, rotate right R7. arithmetic shift right. So you just specify the register and you have the instruction in front of it. So 11 bits of it is an opcode and the 5 bits is the operand side. Then we can see the examples related with the single register, direct examples, complement, negate, increment, arithmetic shift right, logical shift right, rotate right, decrement. These are just some of these examples. And as you can see again, their opcode starts with 10001 and their second part is also 010. The operand is coming in between as a 5 bits. So we can cover all the GPRs 0 to 31 and then these are changing as you can see from the last bit to the second bit and so on. So only the last 4 digits are changing depending on the instruction. So this is known as a single register direct example. The next is the single register immediate. Immediate means defining a constant. So we have got a destination register like a GPR again, and this can be between 16 to 31 of the GPRs, as we already said with the LDI and DI functions. So it's also one word, which is 16 bits instruction, and it's 1 cycles. So the constant is an immediate value, which is an 8-bit. So NDI, LDI, these are given and as an example, and they all have a different opcodes, as you can see. The operands are given in case, capital case, and the destination is in between. Just the 4 digits, it's enough because, as we already said in the previous chapter, 16 starts from 0000 and it goes up to 31, which is 1111. The 5th bit, which is always going to be 1, is not included in these instructions. And this is known as single register immediate instruction. By the way, if you have any questions related to these, please note those down and you can ask me during the live lecture. Next, we are going to cover register pair immediate data addressing. Now, what is register pair immediate data addressing? We have got 2 pairs. I don't know if you do remember add immediate word, which you need to cover 2 registers, 24 and 25, or 26 and 27, or 28 and 29, or 30 and 31. So instead of having a single register, we have got a register pair because it is going to store a word into that pair. So that's why we need 2 registers, because each of our GPRs are 8 bits. We need a register pair to store 16-bit word. And the instruction is 1 word. The cycles are 2. And the first is the operand is the 4-register pair, as stated above, and the second is the 6-bit immediate constant. So over here we are using 6-bit constants, and that's register pair. So this comes in a way that is, as you can see from here, when you have the opcode, you have the immediate value and the destination. So it specifies 24 and 24 plus 1, 25, for example, or 26, 26 plus 1, 27. So this is how they are located in it. And if we look at the machine code, now over here, as you can see, starts with 1001, 011, 011. Now only the last bits are changing over there between add and subtract immediate words. The constant and the destination part. So the DD, as you can see, 24 start with 00, 25 is going to be a pair of that. So 26 is 01, 28 is 10, and 30 is 11. And the KK is just the constant or the immediate that you want to define, which is between 0 to 6 to 3. So once again, as we have a common opcode fields, it makes the decoding hardware simpler. So only one bit different in each of these opcodes. So you just need to know that these values are belonging to the register pairs for DD, and that's what you need to use. So another different categories, two registers direct. Now, in this case, it's not a register pair. We have two separate registers. So, for example, you want to add two registers together, subtract, add them, move them, copy into each other. So we have to specify two registers that you want to make an operation through them. So that's why we have got two registers direct instruction. And the 6-bit of it is an opcode, 5 bits is the destination, and the 4 bits, another 5 bits is for the source. So as you can see from the diagram as well, these are any GPR can be specified between RR and RD. So if you look at these examples over here, CPC, SPC, add, compare, subtract, add bit carry, and they're all two registers specified over there. So we have to specify two registers in the GPR to perform this operation. Once again, the opcodes are similar, only one bit changing at a time for different operations, and they are 5 bits to represent the GPR register address. So memory direct addressing is one of the important ones because we are going to see some indirect addressings as well, and we are going to compare them in this lecture. So with the memory direct, we can actually do an access to entire memory using either direct or register indirect addressing modes. So the first operand is a GPR address, and the second operand is a direct data SRAM address. If you do remember LDS and SDS instruction in the previous chapters that we have used, we can specify the address of the GPR, and we can specify the address of any part of the data space from 0 to RAMENT, which is normally FFFF, which is a 16-bit address, and we can specify any of those, and we can copy data from one to another. So if you do remember, I'm just going to give another example. LDS R19 0hex 560. So what we are having is we are going to copy the value in hex 50, any data address, which is given over here. So this is the part of the data memory, and that has to be copied into the GPR. So, or the reverse operation of that is STS, if you do remember. So we have to specify the address of the data space, and then we are copying it from the GPR. Okay, so their position of the operands is changing based on the instruction that we are having. So the 16-bit address and this address is between 000 goes up to FFFF. So memory, this is important. Memory does not support immediate addressing mode. So to move data into internal RAM or to I/O register, we must first move it to the GPR between R16 to R31 to define an immediate value, and then move it to the GPR to the memory space using STS instruction that we have given over here. Okay, so first we have to load immediate into GPR 16 to 31, then we can copy it to any part of the data memory. Now, and then we have said that similar to the memory direct, which we have seen these instructions, 0 to 31, K is between 0 to 65,000 for the whole data memory. So you need to have a 16-bit. Some of those are outcodes, the operands, and the address for 65,000. Now, similar to the memory direct instruction, we have got IO direct. If you do remember, when we want to use in and out instructions, we can actually use the IO memory address from that bank, if you do remember, IO registers. So this is also one word and one cycle. So source or the destination is a general purpose register between 0 and 31. It can be any GPR. And the destination is actually going to be the IO register or the source. So IO register is from 0 to 63, if you do remember. And this is directly can be like, for example, in R18 0 hex 16 or out 0 hex 15 R18. Now hex 16 belongs to pin B on IO register, and hex 15 belongs to port C. You can find them in the datasheet, you can find in the lecture notes. You can look for them. So only these instructions are using IO direct addressing. So whenever you want to consider this addressing, you have to check the IO memory to find their address, not the memory address, the IO address to use these instructions. That's why the IO register have two addresses, IO and data memory address, and IO address is used when we use IO direct in and out in addressing modes, and the data memory address is used when we use the direct addressing mode, which is LDS and STS. So standard IO addresses can be accessed using both direct and the IO addressing. This gives us a flexibility. But in the IO direct addressing mode, the address field is just a 6-bit address and can take values from 00 to 3F. You can see that from the IO addresses as well, which is from 00 to 63 in decimal. So it can only address the standard IO register memory. And if you want to access the extended IO register, we can just use LDS and SDS, which is a direct addressing mode. Now, the next thing that we are going to consider is the memory indirect addressing, which is also important. And we might ask, why do we need indirect addressing as we have got a direct addressing over there? Actually, we can use anything we want in here, but it's an important if you are using indirect addressing, it's really important in AVR because it uses a pointer and it points to the three registers that we have got in AVR: register X, register Y, and register Z. And these are 16-bit registers, and they are allowing us to access entire 65,536 bytes of data memory space in AVR. So this is, let's open a new page. So as we already said, three registers are used for this indirect addressing modes, which is X, Y, and Z. Now, these are the combining of two specific GPRs. So if I can draw this, this is like a huge register, okay? So if we divide by 2, so X high, it's actually the register R27, so 7 down to 0, 8-bit, and X low is register 26. These are allocated, so you cannot change them to any other register. So these are the only 3 registers that we are using for indirect memory addressing. And the same applies for Y, but this time it's R29, R28, 7 down to 0. So this is known as YL, Y high, and Y low. This is also 7 down to 0. Then we have got the third one, which is a Z register. That's also 7 down to 0. This is known as X high and X low. So R31 and R30 are the 2 GPRs that we are using for register Z. So how they are forming actually, oops. So they are one words, 2 cycles, source or destination registers between 0 and 31 in the GPR. We can use LD and ST. So load or store instructions can be used for memory indirect operations. And if you want to store something into, for example, XL, you can just say XL over there because this is already defined in the include file. Or if you want to define something in XH, you can just specify that XH. So this is actually how we can deal with it. So let's give an example. I think it will be good to have an example to understand what is going on over there. Let's say we have got load R24X. Now, what does this code actually tells us? It tells us that load into R24 from location pointed by X. So whatever we have got the value inside of that register X, that will actually the pointer. So that's the content of X is actually pointing where to load the data from. So that means with the load, it means the read the value of a location pointed by the register. So let's give an example. So following program loads the contents of locations 0 hex 130 into R18. So if you want to load the contents of location hex 130 into R18, what we can do, we can start with LDI XL. So we define the low byte of the register at X. It's going to be X30, so this part. Then we do LDI XH, which is going to be 0 hex 01, which is this part of the address. So high byte and the low byte are defined separately. Then we just use load instruction. R18 with hex. So what does that mean? Copy the contents of location hex 30 to R18. I hope it's clear. Once again, the first instruction loads R26. This is R26. The low byte of X with hex 30, and then R27, the high byte of X with hex 1, and then we copy the contents of the this 130 into R18. So we can give another example. Let's say write a program that stores the contents of R23 into location hex 139F. So store the contents of R23 into hex 139F. Now in this case, LDI, we can use any register if it doesn't specify it. So I'll use Z register. So Z low will be the low byte of the address, so which is 0 hex 9F. LDI ZH, it's going to be the high byte of the address, which is 13. Then what we do, as we want to store the contents of R23 into this location, we just say store Z R23. Now, why do we need to do that? You might ask, why do we use indirect addressing mode? Now, the advantage of indirect addressing mode is that it makes accessing the data dynamic rather than static. So we can use dynamic registers and we can access the data. So I'll show you a good example to understand why it is more useful than direct addressing. So let's write the code first. Write a program to copy the value with hex 55 into memory locations 140 through 144 using A, direct addressing mode, B, register indirect addressing mode without a loop, and C, again it's register indirect addressing mode with a loop. So we are going to cover three examples over here, three programming examples to see how we can do that. I'll just cut this question down over here. I'll just say example. Okay. Now, so if we start with A, it says use direct addressing mode and copy the value of hex 55 into memory locations 140 through 144. So let's start with A. What do we need to do? First, as we are going to use direct addressing mode, we have two instructions, LDS and STS. So if we want to copy or store something from a GPR into the memory location, we have to use STS instruction. Now in this case, we start with LDI, we define one of the registers to hold the value 55. So 0 hex 55 over there. Then what we need to do, we use STS instruction and we start with the address 140 and copy the value of R17 into 140, then copy the value 141, and then STS 142, R17, STS 143, R17, and STS 144, R17. So this is direct addressing mode, and we just use STS instruction because we know that it has to be stored between the locations 140 to 144. We just use STS for each of them, and we can just store the values over there. You can use a loop over here as well. Without any problem, you can define a counter, and as you are going to store it into 4 locations or 5 locations, you just decrement the counter by 5, and then you end up by storing the value of R17 into these locations. Now, an alternative way of doing this is using memory indirect addressing without a loop. Now, with an indirect addressing, what do we have? Again, we have to define LDI. Let's use R17 again for 0 hex 55. Now, we define the constant value to be stored. Then we have to specify the address. Now, we are going to do this indirectly, so we can just say LDI, yes, use register Y, low is going to be, so it's 140, right? So we have to get the 40 into the low. So 0 hex 40 in the low, and LDI YH 0 hex 01 into the high byte. Okay, so maybe I can write the comments for this just to make it more clear. We can say that load R28, which is register YL, with a value 0 hex 40, which is the low byte. Now we repeat the same thing. We load R29 with, oops, that's not load. Load R29 with value 0 hex 01, which is in this case is the high byte of address. That's 29, and that's going to be the high byte of the address. So that's what we need to do first. We specify the indirect memory location. So we use register Y in this case, which is going to hold the value 140 for that memory location. Then what we do, we need to use store instruction. So store Y R17. So R17 value will be stored into 140 as a beginning. Now we can say that copy R17 to memory location 0 hex 140. Then what we do, we increment Y, L part, because that's going to change to 41 now. Okay, so increment YL. So increment the low byte of y, in this case, is going to be 0 hex 41. Then what we do, we store again. So store y r17, and we can say that copy r17 to memory location 0 hex 1401. And then we increment YL again, the low byte. So that's it becomes increment, let's say increment the pointer. And that's going to be 0 hex 142. And we have to store Y into R17. So copy R17 to memory location 0 hex 142. And then increment YL. So we increment the pointer to be 0 hex 143, and then we store R17 once again, and that's going to be copy R17 to memory location 0 hex 143. And finally, we increment once more YL, and that should be increment the pointer 0 hex 144 and store R17 into Y. Now, as you can see, okay, we can write it easily, but it takes ages, first of all. And on the other hand, why do you need to do that? When you have a chance of doing a loop, and when you have a chance to do some auto increment kind of things, which we are going to see now. So this is another way of doing this. And the final version, which we are going to use a loop, it's more pretty straightforward and easiest way of doing or using memory indirects. Now, in this case, let's say see over here, LDI R17 0 hex 55. Now we define that again. LDI R20, we need a counter, so let's make that counter. Okay, to be 5. Let's use it as an hex. Now we have got R20, and then we do LDI YL. Again, we load 40 to the low byte. LDI YH, we load 01 to the high byte. So we have got all the address over there. Then what we do, let's actually tap this first because we need some indentation over there. L1, it's going to be store y r17, which is the same thing that we have done over here. So we copy the contents of R17 to the memory pointed by Y. So let's write this as a comment. Copy the contents of R17 to memory pointed to by Y. Then what we need to do, we have to do and increment YL. So that means increment the pointer to the next one, and then we have to decrement the counter because we have to stop after 5 times. So that's going to be R20, and then branch not equal L1. So if it's not 0, carry on until we finish. So 5 down to 0, it will be counted. Okay, so this is how we can do an indirect addressing, and we can use with the loop. So 140 will have hex 55, 141 will have 55, 142, 43, and 44. They all have the hex 55 value in there. Now, if you have any questions related to this, please note it down and you can ask me during the live session. We have seen these examples that we can use indirect memory addressing with just a loop, and we can easily sort things out. Now, I just want to point out something. These pointer registers, X, Y, Z, they are a 16-bit registers. So that means they can go from the address 000 to FFFF, which covers the entire 64K memory space of the AVR. Now, over here, when you use increment YL, this will actually, what do you call, it will not propagate the carry into the ZH register. There is no ability of the AVR that they can do that. So AVR giving us an alternative option of auto increment and auto decrement. So they overcome this problem by using their auto decrement or auto increment, so they can control what's going on. Because if you are incrementing YL all the time, and when you filled out the first 8-bit, it's not gonna get that carry and pass it to the high byte of the Y. So instead of having that, we can just use auto increment. So I can just draw this auto increment to show how we are interpreting that in AVR. So let's say we have got the register 15 down to 0. It can be X, Y, or Z register. Now we have got the data space. It can be any place in data space. So 0 to Rament. Now, the only thing that we need to care, we have two options over here. Either we do a post increment, or we can do a pre-decrement. So these are the two options that we can have. Now, if we want to do a post increment, we can just have is here somewhere an adder, which this one comes down, okay, and this is just going into there. Then we post increment it. That means we add 1 after we supply the address, and that goes back into over here. Okay, so this is a post increment. We first provide the address to the data space, and then we increment y. And an alternative way of doing this is pre-decrement. So it's similar. We first decrement the address, and then we provide it to the data space, x, y, or z again. So that's our data space. Again, we want to point out somewhere here. Now this time that goes in, that comes from there. We first decrement it and then provide the address. And then that goes back in and we can point out to the next address. So this is how we can deal with post increment and pre-decrement. And of course, the syntax is going to change a little bit, which we are going to do an example to show that. So for post decrement, now in that post increment, let's say we want to load RD, and then like we were doing it, rather than saying X, we say X plus, or load RD Y plus, or store Z plus RD. So these are all the valid statements that we can use, and their X, Y's can be changed based on the usage. And for the pre-decrement, this is going to be load RD minus. So the operation changes. It comes to the in front of it. Load RD minus X and ST minus Y RR. So these are the cases that we can use. And we are not strict with this. It can be changed. Okay. Now, once again, why are we doing this? When we use the instruction increment ZL or YL or XL, this will not going to propagate the carry into the Z high or X high or Y high register. So in order to overcome this issue, AVR is giving us the option of auto increment and auto decrement for the pointer register to overcome this problem. I hope it's clear now. And if you have any question, once again, feel free to ask in the live session. Now, we are going to do this again. I'm going to show you an example so that it will be easier to understand of what we are doing. And let's have more space. So example 2. So it says write a program to clear 16 memory locations starting at data memory address 60. So we have 16 memory locations that we need to clear it out, starting from address 60. Now, if we are going to use post increment or pre-decrement, in this case, we can use post increment starting from 60. So what we can write, LDI R16, it's going to be the value that we want to clear, so 16, so that's going to be our counter. Then LDI XL is going to be the least significant byte, so the low byte, which is 0 hex 60. And that's going to be our XL equals low byte of address. Then LDI XH, it's going to be 0 in this case. And that's going to be XH, which is equivalent to high byte of address. Now, we can define another register, LDI R17 to be 0. So as we want to clear, we have to make everything 0. Okay? So in this case, what we need to do, let's use tabs. L1, it's going to be store X plus comma R17. So that means R17 is going to be stored into X, which is starting hex 60, and incremented automatically. So we can say that clear location X points to. Then we decrement R16, we decrement the counter, and then BRNE L1. So jump back until we reach to 0. Okay, so this is how we can use a post decrement. It's quite useful and easy to deal with it. I want to do another example because these are important. We have to cover as much as we can. So example 3. You can try these by yourself just to make a practice. Write a program to store the following hex data into memory locations. $240 to $243. And then add them together and place the result in locations, in this case 220 2 and 221. This is a good question because we have to deal with a couple of separate things, couple of different instructions, and it will be a good example. Now, the first thing that we understand from it, there's an hex data in these locations, 240, 243, between 240 and 243. And then we have to add them together and we have to place the result. So I'll give you the hex values in these locations. So 240 is 7D. I'm just assuming these values. 241 is EB, $. Then 242 is C5, and 243 is equivalent to 5B. So these are the data that's stored over there. Now, what we can do is, as we are going to store the results to the locations 220 and 221, we can practice equate over here. So dot EQ is going to be the low byte of the address that we are going to store. So we can say this is 0 hex 220, and dot EQ high byte, it's going to be 0 hex 221. Now we start with, let's give a tab. LDI. Now how many locations do we have? We have 4 locations, so let's set the counter to be 4 that we want to read. R16 4. Okay, and then at the beginning, let's say LDI R17 to be 0. Okay, and then we need another one for when we increment it. So we initialize 2 separate counters that we are going to use. I'll show you. One of them is not a counter actually, but we will need them. So now LDI XL is going to be 0 hex 40. So we have to get the low byte of that address. And then LDI XH, it's going to be 0 hex 02. So the high byte is 2. Then what we need to do, we have to load, let's say, R20 with the value of X plus. So we have to read the contents that the X is pointing into R20. Then what we can do, we can say add R17 and R20. That means we are adding the first value. So we are going to store the addition into R17. Okay, so we initialize R17 to be 0, and then we start to add the values in there. So the first value is 17. Now in this case, R17 is going to be equivalent to 70. Okay, so we got the first value and we add it into the R17. Then we check branch, carry, clear. So when we add them together, if the carry is 0, we have to jump. So we have to jump to decrement the counter. So branch if c is equals 0 to decrement the counter. And we have to decrement the counter. I'm just going to do it over here. L1, it's going to be decrement R16. Okay, now if it is not branching, we have to increment R21. That means the carry is 1. Okay, so that has to be the high byte of it. Or maybe just to make sure that we have got the right thing. So let's do that R20 and let's do that R21. So it's easy to manage with these 20, 21 as well. So let's change that to 22. Okay, so we add the low bytes first. Okay, and that should be 22. Now we branch, we increment the high byte if there's a carry to the next one, and if not, we just decrement the counter. And again, of course, we have to check BR any if the counter is 0 or not. BR any L2, and that has to go back to the load. So L2. Then once we have finished this, that the counter is 0, we have to store these R20 and R21 values into these two locations. So we just need to use store, and we already defined those locations and the low byte and the high byte. So I'll just say low byte, which is going to be the R20, and store high byte, which in this case it's R21, which is the flag, based on the flag. So this is the way of doing multiple things together. So first, once again, we define low byte and the high byte that we are going to place the result. Okay, so first 8 bits and the second 8 bits, no significant bits. Then we define the counter for 4 positions, 4 addresses that we are going to receive the data. Then we define the memory location, which is 240. So the 40 is the low byte and 2 is the high byte of it. Then what we do, we start to load the content of this one into R22. So R22 started with a with 70 in this case, and then that 70 is added into R20. Okay, so let's say R20, that is 70. Now we check if there's a carry flag. If there's a carry flag, we have to, if there's no carry flag, we just decrement the counter and we go back and start again. But if there's a carry flag, we have to increment the high byte of that address location as well, because it's going to be more than 8 bits. So we increment that one and then we decrement and we go back and start again. So we have to do this 4 times. So once we are done, this is going to store R20 as a low byte into address hex 20, 220, and R21 to the high byte, which is the address 221. Now, I hope it's more clear with this example. It's a good example to understand how these are operating with indirect addressing and the post increment together. And once again, if you have any question that you would like to ask, feel free to ask in this session. Right, so there is another method which we use. You can find these details in the slides as well that we already covered. So these are the instructions, memory indirect examples. So load RDX. If you want to use post increment or pre-decrement, you can see the opcodes over here. There's a little bit difference on the opcodes, but there are similarities as well. So you can find these instructions in the datasheet as well. So the next one is the memory indirect with displacement. So this is similar to the indirect addressing. So suppose that you want to read a byte that is a few bytes higher than where the Z register points to. So to do that, we can increment the Z register so that it points to the desired location and then it reads it. So we can use the register indirect, which is easier compared to what I described with displacement. And in this addressing mode, there's a fixed number is added to the Z register. So we use LDD and STD instruction. It's one word and it's 2 cycles. So the second operand is implicitly one of the Y and Z registers, and the third operand is a displacement constant. So for example, what we can do, the instruction is LDD, for example, LDD RD Z plus Q. Now, if we want to read from the location that is 5 bytes after the location which Z points to. So what you can do is load R20, which is Z plus 5, or store R20, store it's other way around, store Z plus 5 R20. So Z is the address which is pointing to, which we already gave a couple of examples, plus 5 from that address after the location of point Z is pointing to. Now, Q can be a number between 0 to 63, and RD is just any general purpose register, GPR. So you can see how this is operating. So we have got the Y and Z register. There's an opcode and the 6-bit, the Q. So how many bytes are after the location that you want to read. And you just specify that in Q and you can perform that operation. So that's all about the indirect displacement, and I can show you the opcodes for that operations. LDD, STD are those two, and it can be Y plus Q or it can be Z plus Q. Now you can see their opcodes are similar again. The Q is over there, starting with the 1 bit over there, 2 bits over there. So load and store has a distinguish with the opcode over here. Destination or RR is the GPR, and the rest of the Q is written as the last 3 bits of that opcode. Okay, so another important addressing mode that we are going to cover is a program memory indirect. So this is an addressing mode widely used to access the data element located in the program space rather than in the data space of the AVR. Okay, be careful, the program space, not the data space. Now, program memory constant addressing, we have got two versions of this actually. One of them is just the constant addressing. So the contents of the Z does not change when the instruction is executed. So we can just use an instruction LPM RN Z. So LPM is the instruction that we use to load from the program memory, or we can use SPM, which is used for store from program memory. So load and store from PM means program memory. So we can use either implicit or GPR address for the second operand. And we normally use Z register for this purpose. So if first operand is implicitly R0, then the instruction does not have any operands. So it is using implicit addressing for both source and destination. This is one word and 3 cycle instruction. And this program memory addressing, it also has a post increment version, which we call it auto increment. So you can just use LPM RN Z plus. So the contents of Z increments after each execution, like we have done it with the memory indirect operations. It's similar. Now, the only thing that we need to take care over here is that the program memory content addressing. Now you can see the Z register. The Z register least significant byte defines if we are going to read the low byte or the high byte of the program memory. This is important. So in AVR, each location of the program memory is a 2 bytes, as you can see, 1 byte, another byte. So we have to mention if we want to read the low byte or the high byte. So the least significant bit of the Z register, which is shown over here, indicates whether the low byte or the high byte should be read. So if this least significant bit is 0, then we read the low byte. If it is 1, then we read the high byte of that data. So I can show you a simple example on this to make sure that you understand how they are stored. I don't know if I can fit it over here. Maybe we can do it on here. Now, the low bytes, let's say low, and we have got the high bytes. So the low bytes, let's say, starts with 000. The last bit of that, which I'm going to separate it, it's going to be our low byte of the data. And then for the high byte, we are going to have 001. Okay, and let's say this is address 000. Then once again the low byte in this time, so that's 0, this is 1 for the high byte. So register Z least significant bit is defining that. Then it goes to 1 0. This is again 0. And next one is going to be 1 1. So this is address 1. And then let's do another one, just to make sure that you understand. Again, as you can see, the least significant is always 0. And this is going to point out to 1 0 1. Okay, so 1 3 5 and it goes, and the address is 2 in this case. And it goes. So this is how we can store into the program memory, and I'll show you an example, for example, for a moment. So to read the low byte or if you want, we can write something like this: LDI ZH high so 0 hex 0005 and LDI ZL low, which is going to be 0 hex 0005, and then LPM is R16 Z. So we load ZH with 00 and we load ZL with 05, the low byte of the address. Now, as you can see from this one, or as you can understand from this one, the way it was on the addresses. So to read the low byte of each location, we should shift the address of that location 1 bit to the left. So for example, if you want to access the low byte location, let's say 0B 01010 in this case. So what should be the address? That should be, as it is shifted, it has to be 0B 00001010. So to read the high byte, we shift the address to the left and we set bit 0 to 1. Okay? To access the low byte, once again, we should load Z with the shifted to the left. Okay? And then we put a 0, as you can see. This is just shifted, and we just put a 0 over there. And if you want to read the high byte, we shift it to the left, and we set this bit to be 1. And to shifting, we can use this shift directive, which is like a arrow over there, sorry. Okay, so if you want to shift a binary, we shift it left. If you want to read the low byte, and we'll put a 0 for low, If you want to read the high byte, we shift left and we put 1. Okay, repeat, least significant bit has to be changed to 1 for high byte, and we use shift directives as arrows to the left. So, for example, let's say the program reads the low byte of location 100. So LDI ZH, it's going to be high byte of it, which is the location 100. Shift it 1, and then LDI ZL low 100, shift it 1. Okay, and then LPM R16 Z. So the high bytes and the low bytes can be read like this, and we can easily get the contents of the Z and copy it into R16. Or we can use a OR with a 1, so it bits will be set, 0 will be set. So in this case, what we can do, we can just do LDI ZH high $100 shift 1 or 1 in this case, and LDI ZL low $100 shifted 1 or 1. So we set bit 0 to be 1. And then what we say, LPM R16Z. And that's it. So this is how we can deal with the program memory, how we can store the data from the program memory or load the data to program memory. I hope it's clear. Once again, if you have any problem, do not hesitate to ask. Now, so far, we have seen that program memory, indirect, program memory, data memory, indirect, direct, and different types of it. Now, we will carry on with indirect program addressing. Now, we can also call this implicit, since the source register is not explicitly stated, but it's iJump. So it's like a jump, but it's implicit jump. So we don't know where to jump. It's hidden over there. Again, it's one word and 2 cycles. There are no operators. So in that case, Z register is the implicit operand. So whatever we have got in Z register, it has to jump based on that. So the direct jump or call instructions are 2 words, which are 3 cycles, and their operands are 22 bits, because we can jump to anywhere in the program memory. Okay, so we can use the jump and call instructions as we have seen before as well in the previous chapter. So the opcodes are similar. So the operands is changing over there. Their opcodes is differ by 1 based on that. As you can see, 1 bit is changing for jump and call, and the rest is just the operand in the program memory that we can jump from. And there is also relative program addressing, which rjump and the branch instructions are belongs to the category. It's 1 word and 2 cycles again. The operand is 12-bit. So they have to have the program counter +1 plus the operand, which we already seen this with this how they are operating using the program counter. As the program counter points to the next instruction, it has to get the next instruction count and plus the operand value. So the operand is 7-bit in this case. So more or less, you know how these are dealing with these instructions from the previous chapter. And so we can say that we can generalize the things. So observations on AVR code, two register directs, they're not 0, 0, 1, 1. So single register emit, they start with 0, 0, 1, 1. They both start with 0, 0. Program or relative unconditional starts with 1, 1, 0. And program relative unconditionals again with the conditionals, not unconditionals. They are all 1, 1, 1s, and the rest of the opcodes is changing. So why are we showing this? When you start looking at these assembly codes, you start to understand if they are using any of these addressing and which ones are they using. So we can distinguish them by experience actually. So if you look at this disassembling example, which we have done something similar to this, and the machine codes and the contents in hex are shown over there with their addresses. Now, if we convert them to binary, this is where so it's E is 1110, then 001, and 0000, and it goes like that for all of them. So we just converted them to binary like we were doing in the logic design as well. So how are we going to disassemble that? We have to understand which opcode belongs to which addressing node, which we are already seeing that. So from that addressing modes, you can understand which instruction is used, so you can find out their opcodes and their operands and so on. Now, as you can see, the red ones are single register immediate because it's 1110 gives us, as you all know, it's LDI or ADI or sub-I or whatever they are. And 1001, which is the green one, it can be implicit, it can be single register direct or register pair. So we don't know. So we have to find that out. And 111 is a relative program. So it's conditional. So we have to find that out as well. So you can distinguish these things like from this. The purple one, it's the most memory load stores start with this. Okay, and memory load instructions bit 9 for load and 1 for store. So you can check that from that as well. And on the other hand, memory indirect instructions, they start with 1, 1. Okay, and 1, 0. So 1, 0 for X and 0, 0 for Y, for Z. So you can understand them, which one should be used. And now you don't need to memorize this. We will provide you this, and you can have this from the datasheet. You will know which instruction belongs with an opcode, so you don't need to memorize it. You just need to understand to which instructions to look at when you see these opcodes. I have already done an example in the last lecture, so I'm not going to repeat how are we going to disassemble this code, but if you want, you can try it by yourself. So the first one, for example, is just an LDI instruction. So LDI 1110, then we have got 001, and then we have got 000, and then 000. Now this is saying us that it's going to be R16 as it is 000 for DDD, and that is 10. So what is 10 in hex? It's 16 in decimal. So that means LDI R16. Maybe we can write that. LDI R16, and that's going to be 0 hex 10, or you can say 16 in decimal. They're both acceptable. Okay, then it's 3A0. It's another LDI over there. Okay, so now this is interesting one. LDI, and then we have got 3 and 0, and this is what? 1010. So which GPR is that? If you think about it. So R16 is 0, 1010 is 10. So what is that? That's 30, isn't it? 0, which is R16, yeah, and that's 10 plus is going to be R26. So what is R26? It's actually register XL. Okay, so you cannot do this in instructions, by the way, the parentheses. Either you use XL or you use 26. So let's write that as 26 XL. So XL, and it's going to be 30. So 0 hex, 30 is the value. And let's change that one as well, because this is not valid. Either we use 16 or we use hex 10. So in this case, it's going to be, let's use 16 as it is going to be counter. Now then, there's another LDI, but this time it's one further. So 16 plus 11 is going to be 27, which represent XH. Now, and it's going to be 0, 1. So 0 hex, 0, 1. So that's the third one. The fourth one is another LDI. Now it's 6 and 0, and this one is 12. So 16 plus 12, which will give us 28. 28 is YL, and the value over there is 60. So 0 hex, 60. And then another LDI is there, and that's 13. So 16 plus 13 will be 29, which is YH. And that's the value which is 0, 0. So 0 hex, 0, 0 is given for that. Now we have another instruction over here, which is 1001. Now 1001, we have got 3 of them, which is 1001. Let's check the second part. It's 001. It's 0011. So let's start with this one, which is 001. In this case, it means it's this one, I guess, 001. So we are going to do a load instruction. So LD, now LDX with post increment means we have to have a post increment with X. But what will be the register over there? So post increment with X, we need to find the GPR. So GPR is over here, which is 5 bits. Now 5 bits of that GPR is 0, 1, 0, 0, and 1, 0, 1, 0, 0. So 1, 0, 1, 0, 0 is 16 plus 4, which is 20. That means this is R20. Okay, and that will be where the X points to, so X plus, and it will read into R20. Then the next instruction is 0011. Now it's again, this is time it's store, which is this one. Now 11 is 1001. So that's actually doing R20 again. And this time it's other way, but it's actually store Y with post increment. So that means Y plus post increment over there. Okay, so that's that one. Then the next one is 1001, 0101. So it's decrement. So decrement, we just need a operator over there. So the operand is, the address is 1000, which means it's 16. So decrement R16, which is our counter. And then the last one is branch. So branch is BRNE, nothing else left over there. But where are we going to jump? That's more important. So 0, 1 is given. It's 1, 1. So I'll do that over here. 1, 1, 2 bits. And then 1, 1, 1, 0, 4 bits. And then 0, which is 5 bits. So this looks like it's a in 2's complement form. Because of that, we have to change it to 0, 0, 1, 0, 0, 0, 0. So what's this value? This is -4, isn't it? Now, if we look at over here, this is 108, right? So the program counter is pointing to next address, which is 109 after BRNE. So now we have to go back 4 steps. So that's going to be 018, 017, 016, and it means that we ended up one, two, three, 4. Okay, so 4 step means this is going to be jumping back 1, 2, 3, 4, which is 105, which is over here, which was LD. So that means, let's say this is L1, if we jump back to L1. Okay, so this is how we can disassemble, which we already done this yesterday as well, the last lecture. So I hope it's clear now. And you can see and you can find the similar stuff over here if you don't understand my writing. So the assembler operators which we generally use: add, subtract, multiply, divide, and or XOR, shift left by X or shift right by X. These are all given with an examples in this table. And another important thing is, so when we say the low of that byte, which we are going to get only 34, when we say high, we will just get 1 and 2. So R20 address 34, R21 address 12, which will be pointed out. So we can write it like this as well. Or low -200, you can convert that, the AVR automatically converts that to FF38, and it will get 38 as low and FF as high. Okay, so you don't need to deal with this separate definitions. You can just use low -200 and high to -200, and AVR deals with that for you. Okay, so there are a couple of examples in the slides that we can go through together. And one of them is this programming example. Write a program starting at flash address 0 to copy the value 55 into memory locations 140 to 144. So we already done this in the beginning of this lecture, which we showed indirect and direct addressing differences. So I'm not going to do that again. You can check the code over here. So the counter is defined. So it's used indirect addressing with the increment and the loop. So we define 55. We point out the addresses that we want to use. And then we decrement, increment, and decrement. So rather than using this YL40 and YH1, we can just use, as we defined over here, low and high for the complete address. So this can be changed to low hex 40, 140, so it will just get to 40, and high hex 140, and it will get 1 for the high byte of it. Okay, So these are just some program practices or coding practices that you can use for your assembly experience. And also, we can use a post increment rather than having an increment YL, so we can get rid of that line as well. So to get rid of that line, we just get rid of that and we just put Y plus over here. So that will be replaced and you just have a Y plus over there and we have less code in the program. So that's another alternative and good way of describing it. And we can do an assembling rather than disassembling. So the instructions are given. So based on the opcodes, we can assemble the code based on the given instructions, which is similar to what we have done. So the opcodes are generally given to us. We just need to put them into the appropriate values. So let's do that together as well. So make sure that we understand how we can assemble it because we did disassemble a couple of times now. Let's do assemble as well. So we have all the instructions which is required for this code. So we don't need to look for anywhere else. Now the first instruction is LDI R19. Now LDI is 110. So let's say this is instruction 1. Now for LDI, we can say that it's 1110. Then we have got K, which is the operand. Operand is 5. So the first part is 0000. And then we have got the destination. So destination is 19. Now 16 is 000. So 19 is 3 plus over there. So 0011 will give us 19. And then the rest of the K is 5. So 0101. So that's done. That's LDI instruction number 1. Then the second one, it's R16 hex 55, so 1110. So 55 is 0101, R16 is 0000, and then 0101 is another 5. So that's also done. Now, next one is LDI YL hex 40. So the third instruction is LDI YL hex 40. That's again 1110. Now YL, if you do remember YL, YL is which register? So X is 26, sorry, 27, 28, and Y is 29, sorry, X is 26, 27, Y is 28, 29, and Z is 30, 31. Now, in this case, we have to use Y. So Y is 28 and 29. Now, in this case, we have to load 40. So 40 is 0100 and 0000. So what will be our RD? RD needs to be 28. So 16 minus 28 minus 16 will give us 12. So 12 is what? 1100. Okay, so that's our third instruction. Then the fourth instruction, it's going to be LDI YH, so 1110, which is going to be 1. So this is going to be 0000, and this is going to be 001. Now, YH is 29, so that's going to be 13, 1101. So that's our fourth instruction. Then the fifth one, it's going to be store YR16. So store is 1000, which is starting with that, and then 001. Now we need the R. R is 16, so it's going to be 1001. 0, 0, 0, 0. So, and then we need to have what? The rest of it, which is 1, 0, 0, 0 for the opcode. Okay, so store R16 with Y is given with 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0. Then instruction 6 is increment YL. So increment is 1001, right? So 1001, and then we have got 010. Now the destination is YL. So YL is, as we already said, is 28, which is 12. So now 28 or 12 means it's going to be 0101, okay? And then 28 is 1100, which is 16 plus 12. And then we have got 0011, which is the rest of the opcode. Then instruction 7, it's going to be decrement. So 1001, we are going to use that one. 010, it's going to be R19. So that's going to be 10011. Okay. And then we have got 1010 for the opcode. So that's instruction 7. And instruction 8 in this case is the branch one. So which is going to be 111101. Now, how are we going to find that out? Branch plus 1, it's going to be the value for the program counter. Okay. So if we are going back, that means we have to go back 1, 2, 3, and 4, right? So we need to go back 4 steps. So that 4 step is going to be the instruction with 0, 0, so the KK, and then 4 bits, 0, 0, 0, 1, sorry, 1, 0, and 0. Okay, so 2 bits, 4 bits, and another 1 bit, it's going to be 7 bits. So if we take the 2's complement of that, that's going to be 0, 0, 1, 1, 1, 1, 1. So this is what we are going to store over here. 1, 1, 1, 1, 1, 0, 0, 0, 0, 1. Okay, and this will give us -4 that we need to go back. So that's all that we need to do for assemble the code. So we have seen how we can disassemble and assemble the code. I hope it's clear, and I hope it was easy to understand. Thank you.